straightforward here. I feel like I'm going to be covering a lot of material today, so I might try to move fast. You can interrupt me and ask questions if it's too fast. There's a lot, but it's not too difficult, I don't think. So we left off talking about gray code, right? G-R-A-Y, where you count using the method like we do in our K-maps, where you never change more than one bit at one time. If you expand this to 3, which we haven't done, can you see? Okay, I just want to make sure this isn't in the way. Again, you can never change more than one bit at a time. So if I want to move on to the next number, this one changes, right? So I've changed only that bit. And then I need to start counting up, and we can start puzzling through what that number is. Where did it go? Sorry. I want to make sure I don't skip anything. So gray code is pretty straightforward. It's useful in some applications, but not all. Man. Sorry, guys. I thought I was more organized than this for today. Did we talk about binary coded decimal last time? Do you guys remember? Yeah, so it's pretty easy. It's just that you use 4 bits for one number between 0 and, 4 bits for one number between 0 and 9. So if I want, so I'm going to waste some of the upper bits because 4 bits can cover more than 0 to 9, but it's really easy, right? Like 0, 0, 0 is 0, or is 1, right? So both gray code and BCD, binary coded decimal, are 2 types of encoding. They're one way to store data that becomes easy to manipulate. So we're going to talk some about different encoders and how we might implement those encoders on or in VHDL. There's one other kind of encoding that is really important to be aware of because it gets used all over the place. It's called Ascii. So Ascii is what is used to encode your keyboard. Now technically, what we're using now in the keyboards is Ascii extended. So Ascii is just a 7 or 8-bit, they have 7-bit or 8-bit Ascii. And then they have Ascii extended, which is 16 bits. The Ascii extended is nice because it now allows you to start using foreign characters rather than just the alphabet and the numbers, right? So on figure 10-21, it shows you your Ascii codes. So like in Ascii, and this is they're using the 7-bit Ascii. They're saying that a 1, so the number 1, is represented as this, right? So that table is just saying in the column of 0, 1, 1, it takes the value 0, 0, 0, 1. You can follow down that table so that 2 that's 2 in Ascii, right? So this is one type of encoding that we see a lot in the real world. Whether or not we're aware we're using it pretty much constantly. The 16-bit Ascii is really called, so I guess there's 2. There's Ascii extended, and then there's Unicode. This is also 16-bit. But I think they only show the table for 7-bit Ascii just because those tables get really big when we start trying to be able to represent all available characters that any human uses. We need a lot of bits, right? And I'm still reasonably confident that even Unicode doesn't encapsulate all, say, Chinese characters, because there are just a ton of those. But it does encapsulate all of the Western world characters, which includes, like, right, accent aigu from French, if you took that. Okay, so when we draw an encoder as a schematic, right? So we've talked about how to draw gates in a schematic. Encoders just look like a square box, where they're gonna have some number of inputs and some outputs. So this would be like a 4-to-2 encoder. So let's say, I'm going to just walk through example 10.3 because this is a useful exercise as kind of an all-encompassing idea. So for example 10.3, what they're saying is we want to design a circuit for what we call a priority encoder. So a priority encoder is it converts a one hot number into a binary number with the provision that if 2 or more 1 bits exist in the input, the lower number bits are ignored. So that's what one hot is saying, is that if I have something like that, I don't care about this lower 1 bit. I care about this guy. So our truth table for this is if we have the input, a 4-bit input, and they call it A, okay, so we have a one hot assignment where if we only care about the highest numbered 1. And these are the outputs we care about. So this truth table gets fairly simple, right? So in order to draw a K-map for this, we're going to split this into B0 and B1, right? And draw 2 K-maps for each of these. So what I'm covering here is, right, how to take starting from truth table to all the way to circuit. Now, this is for B1. And this is like one of the easiest truth tables in the world, right? Like we have 2 huge sections of just 8 ones. So it simplifies down nice and easy, and we get B1 is A2 or A3. So truth table, K-map, expression. Yeah.
I'm just, how did you get all the ones? Where did all the ones come from?
So I don't want to spend too much time on it. I encourage you to puzzle through it. It's just because this table, if you fill it out all the way for these x's and just say they're ones, you can end up with a nice fat tons of ones. That's their truth table simplification. I will not give you in a test or anything something where you have to jump from tons of these don't cares to something like that. What's important, the important takeaway here is the idea of if you have a truth table that you understood quickly, could you take it from truth table, K-map, equation, circuit? That's the main takeaway for this. This truth table is a little more complicated than I would expect you to go through remotely quickly. Yeah, because the issue is that we don't have don't cares on this side, right? So if I take this column and this one, and I extend for all values of 1xx, it's not saying that all values of 1 don't care is don't care. It's all values of 1xx is 1. So I have to expand this truth table to say something like values of 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So all 4 of those are 1. Does that make sense? Yeah. So this is a truncated truth table where the 1s extend out for each of the, the 0s or 1s extend out for all of these don't care values. So that's where that truth table comes from. Okay, so we get 2 equations. I'm going to keep this nice and simple. B0 ends up being A2, A1, or A3. All right, let me look at my video, make sure it's all legible. Okay. Once I have equations for B1 and B0, I can turn it into two independent circuits, right? Or tie them together if I have common inputs. So this is a circuit that they come up with in the example. The way I do it, right, is I start out by drawing a circuit for each one of these, where one circuit is just simply A2 or A3, right? A2 or A3. That's one circuit. The other circuit is not A2 and A1 or A3. Now they've jumped to the NAND gate, but we know that the output gate for that logic is an OR gate connected by one ANDed input and one input on its own. The A2 bar is why they threw this inverter here, right? Don't follow that simplification. So that's how we have a circuit, right? And then, are we good if I erase the K-map? Yeah.
So if you want to turn that into a universal NOR gate with circles on the end of those 4 gates and inverters on the end of that?
Yeah, would absolutely work. And then VHDL is as simple as saying, giving some assignment statements where like B0 is equal to, and I could just use the equations that we had before, but we can go from the circuit, right? Well, it's A3 or this, right? And what kind of gate is this? A NOR gate. So I can just say A2 NOR not A1. That's VHDL. So that's how we would go from all the way to the beginning, right? Truth table all the way to VHDL in combinational logic. So now I'm going to try and set up this screen so that we can see some code. So I've tried to make this comically large on my screen, so it should be readable for you guys. Okay, good news. So if you guys want to look at the book, I'm just starting on figure 1027 for some of the VHDL. And what we want to start making here is a priority encoder, which is this one hot idea. So the entity, they want it to call 4-bit priority encoder. I'm just going to call it 4B. The 4B here has to match with this end and this here, right? Inside of architecture is where I would declare signals, but let's start with the port that it wants. So it wants a port called A that is an input of type standard logic. And it's going, it's going to be a standard logic vector. So I can click on that. And we need to specify the size, right, when we're using a vector. So that size is just going to be 3 down to 0. Close that parentheses, end the line, and we have one more port, which is going to be B, which is an output of type standard logic vector, and this is going to be a 2 down to 0. 2 down to 0. I thought this was 1 down to 0. Yeah, 1 down to 0. Right. So now we're looking at a 4 to 2 encoder. On the architecture, we're going to delete this line to keep it compact. It's just going to simply say that I'm going to create a type. Actually, no, this one doesn't want to do the type. Let me make sure I don't screw this one up. Okay, yeah, so we're going to use what we call the conditional assignments, which you guys have seen before, right? So B is going to get assigned to 1, 1 when I really wish these would not be here so that you guys could see them. 1 else Okay, so I'm going to pause here for a second. So this is taking the one hot assignment and putting it into a number between 0 and 4, or sorry, 0 and 3, right? So it's saying that if my highest bit on the one hot encoding is a 1, then my encoder output is 1, 1. Now the structure of this is designed intelligently such that I want to step through 1 bit at a time, starting with the highest bit, because the highest bit takes priority. So the else's only happen if A at 3 is not 1, right? Yeah. Standard logic takes the form of bit vectors, so it can be more than 1. So like B could be assigned, so I could do something like A is equal to, this equal to 1, 1, 0, 1, because it's a standard logic vector of 4 bits. Whereas if it's only standard logic, I could only assign it to A is 1. Yes, it's a vector of standard logics, or an array, or like whatever word you want to use. It's kind of the same idea, right? So the difference between a vector and an array is just that a vector has only 1 dimension, whereas an array can be multi-dimensional. We can create arrays in VHDL as well, but we don't have to. And we can always use that nice old trick of copy and paste, right? And go through because we care about A at 1 and A at 0 and tell it what those encodings should be. I'm not sure what this error is. Oh, I know what it is. I wrote line by line. Sorry, guys. I'm mixing two ways of doing this. Okay, there we go. Sorry. So B is 1, 1, 1, A3, 1, 0. I didn't need to add all those extra B equals. So it's one statement. Okay, so that's one way of doing a 1-hot to 2-bit encoder. So it's 4 bits of 1-hot to 2 bits of binary, right? Simple, straightforward, conditional. There's another way that they can do it, and the main reason they talk about it is creating a constant array. Have we created a constant array in any of things that we've done? Not yet. Okay, so creating a constant means that it's something that won't change, right? And a constant array means I want an array or a vector of constants. So the way we create something like that is we can create something called a type. And these types are something we would call an enumerated type, where if I give it all possible options that it could be, that's enumerated. And we will create this type of, this kind of type a lot. So the type is going to be named Encoder Array. That is just a name that they want to use, or Encoder Array type is what they want to use. And it is an array of 0 to 15. So you'll notice that they're counting up on this one, of standard logic vector 1 down to 0. Okay, a little bit to unpack in here. The name of the type goes first. That's the name that you guys can make up. It is helpful to put underscore type at the end to help keep track that that is the type. Then you say is, what kind of thing am I storing in here? Well, it is an array 0 to 15, so it has 16 elements in it. And each element of that is a standard logic vector of 2 bits. Right? So I've created a 15 by 2 array, essentially. Everyone follow that so far? Then, in order to use that type, I can say something like constant encoder array. So this is, again, a name that I'm making up. The constant is something that's not going to change. Constant encoder array is of type encoder array type. And it initializes the value to, right? That's what this equal sign is initialization. I can initialize it to don't cares on the first one, 0, 0, 0, 1, 1, 0, 1, 1. Oh, wait. 0, 0, 0, 1. We want multiple 0, 1s. I'll walk through this after I get it typed so that I can keep my brain working. What have I done? Oh, the equal sign. Okay, so now I'm just creating the ability to look up what the answer should be. So at the first address, it's going to output don't care. After that, it's going to start defining 0, 0, 0, 1, 0, 1, right? So there's two cases in which I have 0, 1 as the output, right? If I have 1, 0 or 1, 1, right? Because if my highest bit is a 1, I don't care what the other one is. So whether that's a 0 or a 1, I have to output 0, 1. So the address of my 1 hots have multiple outputs depending on, or the same output depending on multiple inputs. The other says if it's not one of these addresses, everything else is going to get filled up with 1, 1. Okay? Now we don't need to use this constant. We can instead, and if you ever want to just ignore code for a little bit, you can right click on it and do this toggle line comments. Now comment it out, it won't do anything. And then all I have to do is say something like B is equal to the encoder array. And when I'm looking at the looking for an element of an array, I need to convert it to an integer, right? So like this 3 down to 0, that's an integer because it doesn't have any quotes or anything around. So we're going to take advantage of the fact that we can convert an integer of A. What don't you like? What library haven't I imported? Standard. My goodness, cannot spell. And then I don't need this guy if I'm using unsigned. There we go. I really like numeric standard, but you don't have this nice convert integer. It has a similar one. Okay, so I take A in, which is a binary number. I convert that to an integer, and I use that integer to look up one of these addresses. Now I have that same 1-hot encoding to a 2-bit number, implemented just in a different way using a thing called constant arrays. Let me make sure my video is still recording. Okay, good. Okay. Any questions on that? If we run out of time, or if we end up with more time, I will come back and we'll talk about how to do like an Ascii encoder. But I'm going to skip that for now because I don't think it adds any new ideas. Oh, it does add one new idea, but I can just say it out loud. So if I have a number where I'm assigning B, say, to a value, and I want to not write out 4 bits of sorry, my mind blank. 4 bits of binary, and this gets more useful. So, because if there's like 16 bits of binary, it could be problematic. So let's create a signal, and it's going to be we'll just call it C because it's not used yet. It's going to be a standard logic vector from 15 down to 0. Okay, so now it's a big one. So if I wanted to assign C to a value, I would have to write out quotation marks and then 16 ones and zeros, right? Or I can use the fact that an X in front of the quotation marks informs Vivado that I want to use hexadecimal. So if you recall from your exam, which all of you got correctly, right? Hexadecimal is just one way of encoding binary. So if I write something like F, 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 what is F? It's just 4 ones, right? So now I've initialized C to using hexadecimal, that's all that X is saying, to all ones. Make sense? Okay. We're going to move on to another idea that we've talked something similar, right? So we've talked about multiplexers that take one of some number of inputs, use a select to output one output. There's another idea called a demultiplexer, which takes one input and sends it to one of n outputs, depending on the select. Demultiplexers aren't anything spectacularly different than those. The book draws out the schematic symbol saying that a demultiplexer is a square. No one does that. Everyone, you remember the kind of the, what is it, the trapezoid for the multiplexer? You just flip that around. And that's really what people actually use for a demultiplexer. Not the square that they've written. I don't know. Yeah, that's not what we use. So a demultiplexer is not really complicated, and I'm not really sure how much it's worth going into demultiplexers specifically. But there is a subset of demultiplexers called encoders. And all an encoder is some sort of signal to a one-hot assignment. So the input is going to be some sort of encoded value. And the demultiplexer output is just going to put a single one on one output to let responding circuitry know which of those codes it is. Let's see. So let's go ahead. I'm just going to start deleting some stuff because it's just as easy to do it that way. Let's see if I need to save any of it. For them, I don't. Okay, so we're going to build up a demultiplexer, right? So the idea here is to get to the point where I can start talking in VHDL as a shared language, right? So that when I describe something in VHDL, you guys can start going, oh yes, I see what that does. So ports, it really just wants a couple of them. E, which is an N of standard logic. Shoot. The auto finish is really obnoxious. I still haven't gotten used to it. S, which is an input of standard. This is example number. It's not labeled. It's in figure 10-36. Let me take a drink. Sorry, standard logic vector of 3 down to 0. And then Y. And they're using .lows. They're like, maybe I'll come back and define it, but I'll see if I can get around it. Spaces. There we go. Okay. So hopefully we're getting used to declaring ports just from the homework and labs. Nothing too tricky about them. And instead of 4b, we're going to call this demux. In order to do that, I have to go change demux a couple of places, right? And then we have to create some code that is going to take the signals from S, which is a 4-bit, right? So there are 16 possible options from S. And I want to turn this into a one-hot encoding, which means if I have 16 possible, I need 16 outputs, right? So this is what we call a decoder, right? This is that subset of a demultiplexer that outputs to a one-hot encoding. So in order to do that, we have a couple of tools that we could go through and do it, right? We could create that constant array, or we could do the conditionals. I'm personally a big fan of the conditionals because they're really easy to read. And to start doing that, we would say something like y at 0 is equal to e when oh, I see why they use the lows. Let me come back to this. So let's say y at 15. Let's start from the high end. So E is the input signal. And when S is equal to 0, else so I flip things around a little bit compared to the example, because in the example, they're doing negative logic and I'm doing positive logic. But all it's saying is, if I have y at 15, bring the input E and store it if S is 0. And then we can step through and enumerate all of those. So maybe I should back this up so it matches the book, just so if you guys go back and look up this, it stays making sense. Y low, right? So we're flipping, E is a inverted input and Y is as well. And then, so Y low, E is flipped, so we're E low. And now because we're flipping things, we're going to start at 0 rather than at 15. And our default, instead of being 0, is high, right? Because we have negative. 0 is now our active state instead of 1 being our active state. So I've made, if we're active, sorry, if we're not active, set it to 1 because that's our deasserted state. That may have been confusing. Did I confuse anyone? No, okay, good. You guys are smarter than I am. That's good. So then in that case, this output would be YL at 0 is when S is 0, otherwise 1. But I have to write 16 lines for this. And that sounds really tedious, right? So we do have a tool in our toolbox called for loops. Okay? For loops can be helpful, but in VHDL, they can also be dangerous. They are helpful when I'm just sitting and writing out 16 lines of the same thing. They are dangerous to use when the for loop outputs and results in some output that is then used in the next loop, the next iteration of that loop. The term we use for that is unrolling. If the for loop can be unrolled and executed all in parallel without any change, it's a good for loop for VHDL. If it can't be unrolled, or it requires the previous loop's results to execute the next loop, it's not a good loop to use in VHDL. And that's because when we turn it into a real circuit, well, we don't do it, right? There's something called a synthesizer that we'll talk about later in detail, is it has to decide how to turn what you've written into hardware. And the only way that it really knows how to do that is to make one block of logic for each for loop that then waits on the output of the previous block. And so I've seen someone fill up the entire contents of a large FPGA with nothing but one for loop. And they're like, why is my FPGA full? Well, it's because it was a for loop and it was like, had like 10,000 iterations and it just, bleh. And VHDL doesn't handle that very well. So this though can be unrolled, right? Because each line, if I went and write the next one, which is YL at 1 is E low when S is equal to 1, else don't do anything with it, right? That second line has nothing to do with the first line, right? There's no so this is where we start seeing usefulness and ability to use a for loop without doing weird things in our FPGA. If we want to use a for loop, we have to use it in what's called a process. So to declare a process, I just write process and say begin. And then I have to say end process later on. So inside of that process, I need to do a wait statement. This process needs information on when it should execute. So I say this wait on SEL. Oh, sorry, SEL. And that what is this thing is if S changes or E.load changes, we can move past this line. If that doesn't change, it's going to hang up on there. If one of those changes, we're going to do for II. So this is something that I highly recommend doing, and they don't do in the book. Anytime you have a loop iteration variable, I double it up. So I use II, JJ, KK. The reason for this is it's a lot easier to debug when you get an error that says error near II, and you go, okay, that's one of my loops. Versus when it says error near I, and you're like, and especially if it's like I clock, and you're like, is it an imaginary clock? Like, what is that symbol doing? So I strongly recommend doing this for debug purposes. So here is how we would do a loop. Wait for this to change. If one of those changes, for II goes from 0 to 15, do stuff, and then end the loop. So 16 times we're going to execute whatever is in this loop. So you can do sequential assignments that come from the what we did before, right? So you could have something like, what was the line? I shouldn't have deleted it. Actually, I think they may leave this for an exercise for you because it requires a little bit of thinking of how to finish the translation. So I'm not going to give you that answer yet because we don't want to do the conditionals quite the same. But this is how you would access the Y low at the index, right? So as this index steps through, Y low at II. So II increments every time we run through that loop. So the first time the loop happens is 0, then 1, then 2, then 3. And we can see how when we have that conditional assignment from before, that is Y equals L when S is 0, you can implement it. Now, they are going to start combining things where they want to use an embedded if statement. So if statements aren't that complicated themselves either, right? So it's just an if statement. If S is equal to, I'll just write this real quick, and then we'll talk about it. So I guess it is an assignment. I really thought it was, but it's not. That's funny. There's a typo in the book. It's missing this end if. So if you start an if, it can be easier to do this type of formatting. I'm a big fan of formatting. I think they formatted it the other way to save vertical space. Formatting is important in your code because it helps me help you debug the issues. If it's hard to read your code, so you'll notice that I start tabbing things in. So weight and for are at the same level, right? So they say the same, but inside the for, I tab it in. If this if statement had multiple lines, I would tab those in more. This is how I want you to make your code. If you're taking 1400 from Gibbons and learning Python, right? Python requires these tabs. VHDL does not, but I highly encourage you to keep that practice. Okay, so all this is saying is, oh, sorry, that is a little bit confusing to do that. This is how I would really prefer it. So if S is 0 to 16, right, as we iterate through. So on the first iteration, if S is 0, then Y at 0 is assigned to E. If it's not, then we assign it to 1. Then we repeat. If S is equal to 1, then Y at 1 is, and so on and so forth. And now we're stepping through and doing this one hot assignment in a for loop. The main takeaway is not writing a one hot for loop. The main takeaway is, can you write a for loop? You guys think you could write a for loop? Okay, that's the most important takeaway from all of this. We go to 1145. Okay. You would think that we would remember that as faculty members, but we never do. So your homework that's supposed to be due today, I will push it out. Yes, I'll push that till Friday at midnight. And yes, because I need to cover test benches better than I have, more than in just lab. It needs to be in a video. So that still has to happen, and I have to talk about a project. So I have mentioned what test benches are, right? So test benches is where we take something and we provide inputs to it and then record the outputs. So let's say that I have this, and I want to test to see if this works. Then all I have to do, let's pop this back into the window. So everything is hilariously large because I blew everything up. If you have trouble seeing your screen, you can increase the font size. It's just in the tools, like the settings. Display, and then font size here. If you want to make it bigger or smaller, this is where you do it. Okay, so I now have a, I'm sorry, this is so tiny. This, oh, I can make this small. This design source called Demux, okay? In order to test that, I need to add a new file called a simulation source. I click next. create file, and I'm going to call it demux_test_tb, test bench. This is how I like to name things, because if I lose them on my computer, I can just start searching for, oh, don't typo them, test bench stuff, right? _tb, and it can help me find files. I just can hit OK. So I could create my ports here. I don't need to, so I'm just going to hit yes. And that will create a test bench source. So the demux is both a design source and a simulation source. So that's why it's in here. But the test bench is what I want to edit. The test bench is going to start with some stuff in here for us, which is nice. And we remember that we also want to keep using IEEE dot standard logic unsigned. And this is just a reminder that VHDL is generally not case sensitive. There is one case that we will get to later that is case sensitive, and it's awful. This is the worst failing of VHDL, is that it has rules like you never blank unless, and those unlesses really get you. In a test bench, you actually don't need any of these ports. I do need to let it know that the component demux exists. The easy way to do that is come to demux and just copy the entity and port, and then come back to the architecture, paste it in, but instead of being an entity, it's now a component, and we have to end component. Let me get a little tab. Oops, tab. There we go. So now the test bench knows that there is potentially a component that exists with the name demux, where it's going to look in the rest of the project for a matching entity, and has those ports. If the ports don't match, you're going to get weird errors that can be difficult to track down. They're not the worst errors, because the errors say will say something like does not have matching port length. So it's not that bad of an error to hunt down. Then we need to create what's called an instance of this component. So we're dealing with this in lab, right? Where you created a component and then when you want to use it multiple times. If I wanted to use a component multiple times, I don't need to recreate new files. I just create new instances. So in a test bench, we call the thing we're testing UUT, unit under test. It is a demux type, and it has a port mapping of, well, I know I need a e.low port. I need a, and I'll fix this later, S port. And I need a Y low port. Okay. At the test bench level, these right now are just ports. I can't connect ports, right? Ports are just something that wires plug into. I have to provide it something to plug into, so I'm going to create some signals for these to plug into. And I'm going to just keep this naming very similar, because you can do this. The net and the port can actually be the same name. This is not necessarily a good idea to do in industry. So a lot of times that you'll see it in industry is they'll do _S. So label that this one is a signal. And its type is going to have to match the port. And I can just, now that I've shown you kind of how to do that, signal, we don't need to call them inputs or outputs because they're signals. Sorry, sometimes I do this in the wrong order. Signal that, right? Let's debug what I have done. Does anyone see the problem that I've done, that I'm missing? No, E is standard logic. I feel like I'm just missing, like I put this semicolon wrong spot and my brain is just blanking, which is not great. Did I use any signals in the other code?
Oh, I think we that we
No, so that this begin belongs, oh, good call. This is just on the wrong side of begin.
I just saw that.
Yeah. Okay, good catch. Thank you. Yeah, so the begin belongs to this architecture. And then the signals have to get declared before that. Too many parentheses on that one. Okay, so now I have signals, and I'm going to rename them with this _s to remind myself that if I see an error, I know it's tied to the signal and not to the port. This is pretty standard for industry stuff. Okay, so now I have a UUT, it's demux, and I need to map each of these ports to where they belong. I'm probably missing an is. Oof. Sorry, I'm being really rusty today. Oh my gosh, I think this is one of those stupid. Yeah, this is one of those cases of you always end a line with a semicolon unless it's in a component. Okay, so now I have one instance of demux, right? And I've mapped the ports that port to signal. And now I need, in order to test it, I once again need a process. And I always begin and end process. Inside of this process, I can do commands like wait for 10 nanoseconds. I can also wait on things or wait until conditions, but let's just wait for 10 nanoseconds. And after 10 nanoseconds, I want to assert that EL is going to go to 0. The other input that I'm going to have is that, oh, what are you mad at now? Oh, ELS. And SS is going to get assigned to, and SS is a standard logic vector, so that's quotation marks instead of ticks, instead of apostrophes, right? And it's 4 bits, so it's going to 0, 0, 1, 1. Then I'm going to wait for another 10 nanoseconds. Again, ending with those. Copy, and I can just paste this a couple of times and make little changes. I could also start implementing for loops here if it's predictable, right? Which is what we will do in our next lab, is we'll actually start using for loops to do some of these tests. So there, this is a rough test bench, right? I'm going to change E, I'm going to change S, and we're going to hopefully see what happens. I just pushed this little dock and float button. It makes it easier to see. Once I have that, I can come over here to simulation and make sure that my demux is underneath the test bench, right? Before they were on the same level, now it's underneath of it. You have to save these things in order to make sure. So if you've made the changes and it hasn't updated, just make sure you've saved everything in your project. And then you just hit run simulation. If you get errors at this stage and you can't understand what they are, I highly recommend running synthesis, because synthesis gives you more defined, clear errors. And if synthesis doesn't give you any errors and simulation does, that means the error is in the test bench itself. Okay. So by default, I can click this zoom fit and it will zoom to the whole thing. You'll notice that a lot more is happening than I wrote, and that's because that process is just repeating, executing repeatedly. At the very beginning here, everything is undefined, and that's because I don't define anything until that 10 nanosecond mark. So if I wanted it to start with a value, I would have to initialize it using that colon equals, right? And then I can start seeing. So if I have 3, and I'm changing EL, and I can go check the outputs for one hot assignment or not. I won't step through and make sure this whole thing has worked. If you need to run longer, you can just click this button that will run for 10 microseconds, or you could change it to run for 1 microsecond. And you just click it and it would run, oops, longer, right? So now I've run even longer. It's just repeating that same process, so not helpful, but if you need to rerun it, that's how you do it. Now, very important thing. If you need to look at internal signals, so say that I have like a top level module and then adders underneath it, and maybe like so top level module, 8-bit adder, and then a couple of 4-bit adders. If I want to go delve inside of those, we call those internal signals. Those are accessed by going and clicking on scope here. A lot of times it'll start off like this, where I will now click scope and then objects. And now I can go out and drag any one of these signals onto my test bench. And now I can start seeing internal signals. So I can see what the units that I'm testing are doing on the inside of things, instead of just the outputs at the test bench level. Very helpful for the debug. Know that, keep that in mind. If you at least remember that you can do that, if you get to the point, you can at least ask me how to do that, right? But remember, that is a very powerful debug tool. All right, so that's test benches. Yeah.
So you said that we're doing synthesis based on hardware.
Yeah.
Okay, so is the test bench part of the hardware, or is it just the way?
No, so test bench is pre-synthesis simulation. There are ways to run post-synthesis simulation, but that's beyond the scope of this. Okay, so I have like 8 minutes left to cram some new information into your head. So upcoming, we have our first of 3 projects. These projects are going to accumulate into a fairly simple microprocessor. This project is, the first one is only a page and a half. It's not very long. I think I've posted it. And what it's going to do is it's going to need to take an opcode. An opcode is just like a command. It's its operation. And you're going to need to be able to do things that are add, do an XOR, load, hold. There will be a table on there when you open up that tells you what these opcodes are and what they should do.
And you're going to have to create a test bench that steps through and sends a VHDL module that you build, an operation code, and I think they're 4-bit inputs, no, 8-bit inputs, and either add them with a carry-in, do some XORing with them, or whatever else. From my perspective, this is a very clear lab. So I didn't write this. This is just something that I yanked from previous iterations of this course. This project seems very clear. We will probably mention this again, but I want you guys to be aware that this is coming up. I think it's, yeah, I'll have to look at the schedule to see where we're at. But this is an upcoming project that I want you guys to be aware of. And at the very least, we can start thinking about what we're headed towards, right? So we're gonna have a VHDL module. It's gonna have inputs, A, B. It's gonna have a carry in because it's an adder. And it's gonna have another one that is operation code. So you're gonna change the operation code and tell this unit what it's supposed to do with its inputs, right? And these are gonna take operations like if statements. If opcode is this, then that, right? And we know how to add. We built adders. We know how to do XOR. We just write XOR, right? All of these things. So I don't think after this lecture, I don't think there is anything in this project that you guys don't know how to do. We will spend lab time doing this. And once we start this, there was on the schedule, there's a VHDL help day that I have skipped over. I'm saving that until we start the project so we can spend a whole day on projects. So I see a lot of you that have laptops. I have that walkthrough on how to install Vivado. If you haven't done that or aren't understanding it, you can ask me during lab time if you bring your laptop. Because it can be helpful to come to class with a laptop with Vivado installed. If you don't have Vivado installed, so I have to make sure that I have a window that doesn't have like personal stuff from like your grades or anything. Okay, let me think about, I wish the schedule would load. It's not going to. 1 second. Fine. Okay. Come on, you're plugged in. You should be happy. This is your backup option. This is just a website called EDA Playground. You can write test bench code here, design code here. You need to set your language to VHDL. But this will do most of what you need to do. The only one that I haven't figured out, so I don't use this very often, I use Vivado. I teach you guys in Vivado because that's what you're really going to use, right? But if you just need something that works. So what I don't know how to do here is how to create different modules. Right, so you can test individual modules, but like where you've created an adder, the submodule, and then you have like a top level. I haven't figured that one out yet. It is probably possible, and it may be as simple as adding this plus button. Yeah. That looks like it should work, and it should be able to call each other. So this is your portable backup. I think that's all I wanted to cover for today. Any questions?
Is there a time today that you have free to go over?
I do not have time today.
You have time tomorrow?
I do have time tomorrow.
Is there any way in this class you've done the homework? Guys, I want to look over it. was it pretty difficult?
It's just confusing.
So I don't know. I'm